Hello everybody! I have good news for you. I've got a bunch of paper, bunch of Sharpies, and most importantly of all, a bunch of time and a bunch of new material. Today, I have something special for you. We're gonna learn Astrodynamics. Which is pretty exciting. For me anyway. I'm taking a class on it right now and it is intense stuff. Like, it's one of my hardest classes, but also one of my easiest just because I love it so much. So it's not a chore to do my homework and all that stuff. But anyway, I'm going to start a YouTube series on it just as we go through the course. Obviously I'm not going to go into quite as much detail as lectures do because, well, it's YouTube, and honestly, who's going to sit through... Well, never mind. There are those people out there, like me. Anyway, let's dive right into it. First, let's talk about the history of it. Okay, way back in the day, I don't know when, maybe 1600s or so, the big scientific question was, okay, how do these planets work? How do you describe their orbits? What's at work here in their motion? And the person who could figure this problem out, they were basically... It was basically as important as solving cancer is now. You know, it was that... Like, if you figured that out, you'd win the Nobel Prize, basically. And so, Tycho Brahe and Johann Kepler were two individuals that made a pretty good... contribution to the solution of this problem. Now Tycho, he was more of an experimentationalist, I would say. He could take pretty good data, fairly accurately with what he had. It was pretty remarkable for the day. And Johann Kepler was a brilliant mathematician and theoretician. And so Johann figured out all the secrets hidden in Tycho's data. And so basically what he came up with are 3 laws, and I'm going to go over them briefly. 1. The orbit of each planet is an ellipse, with the sun at one focus. Previously, orbits had been thought of as circles, and he pretty much proved that wrong. Or whatever it's orbiting. It could be orbiting a planet, maybe this is a satellite around whatever it's orbiting. But the way he stated it was the sun at one focus, because they were talking about planets. 2. By the way, that's the sun. The line joining the planet to the sun sweeps out equal areas in equal times. This one is a little bit confusing, just to read out loud. So basically what's happening is, say a planet's orbiting around here. Here's the angle it sweeps out. On this side it's going to go quicker, so it sweeps out this area. Way over here it's going to maybe sweep out that. It's going slower. So this is equal to this. So, that's what he figured out. 3, his third law, and he came up with this 10 years after the first 2. The square of the period of a planet is proportional to the cube of its mean distance from the sun. So that would be expressed this way mathematically. The square of the period is proportional to the cube of, this is the semi-major axis of the ellipse. So, those are his 3 laws, and his laws didn't address the why of the problem, it only addressed the what. So, you may have heard of this fellow. Isaac Newton figured it all out in his early 20s. But he thought of this as one of his more inconsequential ideas at the time. And 20 years later, Halley, you may have heard of him because of Halley's Comet, or Halley's Comet, some people say, and two other colleagues proposed this bet to describe the nature that causes heavenly bodies to follow elliptical paths. And so Newton is like, oh, I figured that out like 20 years ago. Give me a couple days and I'll go find the proof among my papers. And so it was that this simple conversation brought Newton's greatest discovery to light. So, yep, that's how it happened. And so maybe you've heard of his 3 laws. He has 3 laws to describe motion in general, and his 4th law pertains to gravity. I'm not going to write them all out because, you know, they're so famous and you've probably heard of them if you've taken any sort of physics class. But number 1 basically states an object is at rest or it's in motion, continues in a straight line, doesn't do anything, unless there's this outside external force acting on it. His second law talks about force and acceleration and the relationship to mass. So F equals ma is another fundamental thing you learn in a basic physics course. And his third law is pretty important to rocket science. For every action, there is an equal and opposite reaction. So let's talk about gravity. And we're going to come at it from a slightly different perspective than we usually do, or than you have seen in physics or whatever. We're going to talk about the n-body problem. You might be like, oh, an n-body? What's an n-body? Oh, that sounds kind of weird to me. Well, n number of bodies. Multiple bodies. A lot of them. 2 or more. So, I'm gonna probably just go over the basics with this stuff, because honestly, after we talk about this, we only consider 2 bodies. So the rest of the course after this is like, alright, there's just 2 bodies, and we only deal with the 2-body problem. But you need to know this, especially if you're going to move on and do Astrodynamics 2. So, any satellite can be acted on by many gravitational sources, as well as other forces like thrust or drag and solar radiation, depending on what the situation is. So, the ith body is the spacecraft or the thing you're looking at that's orbiting, the main thing that you're trying to figure out the path of. So, the ith body, mi, that's the mass of it, and so the vector sum of the forces on this body will determine the equation of motion, which is going to be the y, the what's causing this rotation, this weird planetary motion. Okay, so the coordinate system, let's just do a simple x, y, z thing here. And so you've got your thing out here, your mi, your ith body, and okay, you've got an r vector pointing to it. Oh, I missed it. That's stupid. So that's Ri. And put a little arrow over it because it's a vector. And then, okay, just ignore this thing. Alright, and then you've got other bodies out here. M1, M2, you know, let's just do 2 for now. Don't want it to be too complicated. So you got vectors pointing to those, ba-ba-da, dee-dee-dee-dee. And so you've got force of gravity pointing from mi to each of these thingies. Okay, maybe there's another one. Mn. There could be any number of them. Okay? So, remember that picture. When we go to sum forces... Oh, that's a horrible sigma. Whoop, bonk, bonk. That's better. Fg. We use... This is Newton's big moment. You may have seen this in physics. Minus g, that's the universal gravitational constant, times the mass of the ith body, times the mass of given object that's attracting it, and divided by the distance between them squared, and that'll be represented by 1I. Okay? And actually, since we're doing vectors, this is along the direction of R1I, that's J, I, and we only want the direction, so we divide by the magnitude of R1I. Okay? And then we just do that for 2 and 3 and all the way up to n. So G mi mn over rni squared times rni over rni squared. Or no, the magnitude of it. Oops, you can't see it. Okay, we can express this in a much nicer way just by using summation notation. I love saying that. Summation notation. Whoops. Minus G. Ugh. Oops, my head's not in the game. Ugh. Okay. F G is equal to, since G and Mi are constants, they don't need to be in the summation notation. Oh, and by the way, you know why it's minus here? It's because it's attracting, they're going inward. You'll see why when we talk about coordinate systems more. But anyway, and then you sum all of these masses. No, that'd be M1, wouldn't it? Or let's use J. J equals 1 to n divided by r ji squared times the vector r ji over the magnitude of vector ji. So, there we have it, and that's the n-body problem. However, that's not our equation of motion. That's just our summation of forces. Now, when we apply Newton's second law, you know, the F equals mi. By the way, this symbol is vectors. Summation of the forces is equal to the acceleration, or the derivative of momentum. He actually phrased it the more fundamental way this way. And I could show you why it's more fundamentally stated this way just by showing you that, okay, if this is constant, because, you know, the mass could be changing, but it usually doesn't unless it's just a rocket that's thrusting. This is basically... sorry about that, guys. My memory card cut out again. I'm only working with a 2 GB memory card. So, I think I was talking about how Newton's second law can be more fundamentally expressed in terms of a change in momentum. And so basically I'm showing why that is the case, because if your mass is changing, which it often is the case in launch vehicles, you know, burning propellant, the mass is getting decreased. And so, well, I don't even need to write this. You can just see dv dt is a, so that's ma. So it really is the same thing, basically. Where was I going with this after this? Oh yes, we're leading up to the equation of motion, which is what describes the motion. And this is really where Newton won big, because everybody else's approach was they were trying to solve it, like flat out solve it. And he knew better. He basically figured out, he went a step more complex in thought and figured out the why, and it's the force of gravity that's doing all this. And so basically, when you expand this out, what you get, if you know calculus, which I hope you do, is dmi dt times r dot I. The dot is the time derivative, plus mi times dr dot dt, and that is equal to m dot I r dot plus mi r double dot, which the two dots is two derivatives, time derivatives, which is, you know, derivative of r is v, derivative of v is a, so that's acceleration. Now you divide through by mass, mi may be a function of time, and you get the equation of moment, or, I mean motion, moment. I say the dumbest things on camera. R double dot I is equal to the sum of the forces over m, that's just Newton's law, minus R dot I mi dot over mi. Equation of motion. Guess what? Try solving this equation. It's a second order, nonlinear, vector differential equation of motion, and it defies solution in its present form. You know, simplifying assumptions and manipulations are imposed to make life easier for typical calculations. For example, a satellite relative to the Earth. And you know what? We simplify it to the two-body problem. Get rid of those eyes. And, you know, that's a discussion for next time, and the time after that, and everything past this point will be the two-body problem. And we're actually going to work with this and figure out, you know, geometrical properties, mechanical properties, and figure out orbits based on orbital parameters or elements. So this is probably where we're going to stop for this first time here. We made it all the way to the equation of motion, which is pretty important. We can, you know, work with it using numerical methods, but this is where we're going to stop for today, and I hope there will be many more of these videos to come. So stay tuned for those. And now a recap.